Good morning, students. Yes, very good morning, students. Let us we discuss about now real numbers. In that real numbers, mainly we have four exercises. The first exercise, applications of all applications of Euclid division lemma. Second exercise is all the applications of fundamental theorem of arithmetic. Fundamental theorem of arithmetic. And then third exercise is about revisiting of irrational numbers. I mean how to prove irrational number. And the last exercise about revisiting rational numbers in their decimal expansion. Here to proving as irrational number, third exercise. Fourth exercise is about how to prove, how to write their decimal form. So now let us discuss before going to learn about applications on Euclid division lemma. First you should know what is Euclid division lemma. See here, Euclid division algorithm or Euclid division lemma, nothing but one of the application of division algorithm. You know very earlier classes, what is division algorithm? In 5th or 4th class only you know. Division algorithm is nothing but dividend equals to divisor into quotient plus remainder. So this is the division algorithm. Here also a given positive integers a and b. I mean a here nothing but dividend, which is larger number of a and b. A we can write as in the form of divisor into quotient plus remainder, with the condition is remainder should be greater than or equal to 0, but it should always less than b. Then only division algorithm will be possible. Generally we will do. To find what is the use of this Euclid division algorithm or Euclid division lemma? Division algorithm nothing but division lemma also. So here this is Euclid division lemma or division algorithm useful to find the HCF of given 2 or 3 numbers or more. And then after fundamental theorem of arithmetic. What is fundamental theorem of arithmetic? That is, let us take any composite number. For every composite number can be expressed as a product of primes, and this factorization is unique. I mean, we can write any product of any composite number as product of primes in a unique way. Means we can write in a unique way only. We can't write in another way, but order may change. For example, 12 is there. We can write 3 into 2 into 2, product of primes. Order may change, but further the prime numbers never change. So here this is called fundamental theorem of arithmetic. I mean, we can write any composite number as product of primes in a unique way. Means order may change, but the prime numbers whatever exists doesn't change. So from this we can conclude that any composite number we can write as a product of primes in a unique way. Once again I am repeating, students. First exercise belongs to Euclid division lemma or algorithm. That is nothing but one of the application of division algorithm. That is dividend equals to divisor into quotient plus remainder. So here dividend is nothing but if any two positive integers are given, in that big number will be a, small number will be b, we can write as product of its quotient and remainder. Then after condition is 0 less than or equal to or less than b. Then by using this division algorithm we can find HCF of given 2 or 3 numbers. Further you will learn not only 3, 4 also possible. Stepwise we will do. And then after fundamental theorem of arithmetic is every composite number can be write or can be expressed as product of primes in a unique way, and this factorization will be unique. In some textbook it may define like this, and any composite number can be expressed as product of primes in a unique way. Order may change, but our prime numbers never change. We can't get other than those whichever possible. So these two are main concepts. What belongs to exercise 1 and 2 of this chapter, real numbers. So let us complete exercise 1.1, the related examples based on Euclid division algorithm, how to find HCF of two given numbers by using Euclid division lemma, and how to write any composite number as product of as by using Euclidean lemma, how can we write nothing but division algorithm? Let us you learn, and some more applications will learn. What are the leftover problems, either examples or exercise problems, you will get as a home assignment. Let us we continue. First, let us we discuss the applications on Euclidean lemma or algorithm, students. Yes, students, let us we discuss one exercise problem from 1.1, which is one of the application of Euclidean lemma. It is given that, students, use Euclidean algorithm to find HCF of two numbers. So here, first one is given, first bit 135 and 225. Not only two, students, three also we can do by Euclidean lemma. By Euclid's lemma or Euclid's division algorithm. Both are same, students. Euclidean lemma or Euclid's division algorithm. Both are same. No confuse at all. So in general, actually I will explain long division method also, but it is not required, students. If you can do directly. First, what is division algorithm? First you write the definition. So condition is this one. So we should write in this form. A is generally either 2 or 3 numbers are given. A we will take larger number. We are writing 225 as product of 135 as well as some remainder will get 135 to the 270. We can apply trial and error method, friends. 135 to the 270, but we have 225. So let us take 135. 1 the 90 is LCM. So 135 into 1. This is A. This is quotient plus remainder is 90. We should continue this process till you get 0 remainder. In which step we will get 0 remainder? That step, divisor itself is called LCM. Now in these two numbers, 135 larger, so 90. So 135 become dividend. If you take 95 2s are 180, not possible. Again 1s are 90. So we have remainder as 45. So 19 to 1 plus 45. In this step, divisor become dividend, remainder become divisor, continue. So now we have again this step, divisor become dividend, remainder become divisor. So if you take 45 2s are 90. So this step we got 0 remainder. So we should continue this process up to getting 0 remainder. Once again I am repeating, students, no need to do long division. This is a part, this is not a part of problem. How we got these steps to understand, I explained. I just now I said now it is a one of the application of division algorithm. Dividend equals to divisor into quotient plus remainder. Same. We should continue this process till getting 0 as remainder. So we continue. But here we got 90. This 135 become dividend, 90 become divisor, 90 plus 45, 90 plus 45 become again. So we got here 45 that become remainder, that become divisor, 90, 45. So 0 remainder we got. So in this step, which step we got 0 remainder? That step divisor is called as HCF. This is the method to find HCF of given two numbers by using Euclidean lemma or division algorithm. Once again I am repeating, students. For finding HCF, we have mainly three methods. One is long division method. Second one is prime factorization method. Third one, Euclidean lemma. Prime factorization method, long division method you learn in earlier class only. Now Euclidean lemma. So these three methods. For finding LCM, by using prime factorization method, division method, LCM method, and then after by using relationship between HCF and LCM, even after when two numbers are given, it is not applicable when three numbers are given. So this is the process to find HCF of given 2 or 3 numbers also we can continue. When 3 numbers are given, we found HCF. First to find HCF of first two big numbers. After finding that, the HCF of the two numbers and the third number itself is called HCF of given 3 numbers. This is the process to find HCF of given 2 numbers by using Euclidean lemma. Once again I am repeating, students. First write this as product of this, then after we have to, then we will do this, then after we just complete this process This is the way to do. So let us discuss some more problem. Because when we take 196 students, if you do trial and error method, 195 is only possible. So this step only we got. Sometime it may happen like that. In that step, divisor itself is called HCF. This is the process to do. Once again, repeating students, take the larger number of 2 and up by using Euclidean lemma, we can write then after larger number equal to product of smaller number and quotient plus remainder. You just continue this process up to getting 0 remainder. Then you will get in which step it is divisor itself. In which step we will get 0 remainder. That step 0 and in that step divisor itself is called HCF. This is the process to find HCF of given two numbers. Before going to teach, then let us discuss some more problems of this exercise. Then we'll conclude this. Then now show that it is given. Second problem is given that show that any possible odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Q is some integer. I mean, it may be negative or positive or 0 also. So let us discuss this problem. Students, you by using Euclid's lemma, by Euclid's lemma or division algorithm, Euclid's division algorithm, we can write division algorithm. We can write any positive integer is in the form of, we can write any positive integer in the form of 6q plus 0 or 6q plus 1 or 6q plus 2 or 6q plus 3 or 6q plus 4 or 6q plus 5. Because when 6 remainder, again it is 6q plus 0 form. Listen students, whenever we are dividing by 6, first suppose if it is 2, example if it is 2q plus 0 or 2q plus 1. If it is 3q plus 0 or 3q plus 1 or 3q plus 2. If it is 4q plus 0 or 4q plus 1 or 4q plus 3 or, that's it, because 4q plus 4 again it becomes 0. I mean, whenever we are dividing any number by the 2, we get 2 forms. Because 0 remainder, 1 remainder only possible. Other than not possible. Again when we divide by 3, 0 remainder, 1 remainder, 2 remainder, 3 forms possible. When we divide by 4, 0 remainder, 1 remainder, 2 remainder and 3 remainder only possible. After 4 it becomes 4q plus 1. 4q plus 0, sorry. When we divide by 5, it possible 5q plus 0 or 5q plus 1 or 5q plus 2 or 5q plus 3 or 5q plus 4, where q is integer. So students listen, when we divide by any number, that by what number we are dividing, that many forms are possible. By 2, 2 forms. By 3, 3 forms. By 4, 4 forms. By 5, 5 forms. By 6, 6q plus 0, 1 remainder, 2 remainder, 3 remainder, 4, 5. 6 forms are possible. What they said, it should be an odd, positive odd integer. Positive odd integer. So it is given that show that the positive odd integer is of the form this one. What is meaning of odd integer? When the remainder is 135. When we divide by 2, when the remainder is 135, then it is odd number. Here if you observe 6 cube, 6 into multiply any 6 in place of cube, take any integer students. 1 you take, 2, 3, 4, whatever you take, you will get always even number. So when even plus odd only it become odd number. So therefore we can conclude that odd positive integers are in the form of 6q plus 1 or 6q plus 3 or 6q plus 5 for some q where q is some integer, either negative or positive or 0, whatever may be. See students, when we multiply by 6, any number become even. You learn earlier classes, when we add two even number it become even. 6 plus 4, 10. 16 plus 4, 20. 26 plus 4, 30. For example, I am saying 32 plus 2, 30. 32 plus 2, 34. Even numbers means sum of an even and even always even. That means this is an even, this is an even, this is an even. So when we add even integer with odd, that become odd. That is why 6q plus 1, 6q plus 3, 6q plus 5 are odd numbers where q is some integer, hence it is proved. In this case also, based on that case, it changes. So students, please go through that where odd number and which case it is odd number, in which case even number we can use by using the properties of odd integers and positive, even integers, positive odd integers or positive even integers we can prove it. From that we can conclude this one. So let us discuss one more problem, friends. See students, here it's given that fourth one, use Euclid division lemma to show that the square of any positive integer is either from 3m or 3m plus 1 for some integer m. See students, we have to prove square of any positive integer. So first we should write as in the form of 3m or 3m plus 1. Students, when to show it is in the form of 3m, let us write the form of, we can write by Euclid division lemma. Students, listen carefully, by Euclid's lemma or division algorithm, we can write any positive integer in the form 3q or 3q plus 1 or 3q plus 2. Because when we divide any positive integer by 3, we may get 0 remainder, 0 no value, 1 remainder, 3q plus 1, 3q plus 2, where q is some integer. By which one? Euclid division lemma. Yes. Now, but actually we have to prove it square. So let us take case 1 because we have 3 forms. Let us take A is in the form of 3q. We are doing squaring. Why squaring only? Because it is given that short form is SOBS. squaring on the both sides. Then it become a square equals to 3q. It become a square equals to 3q whole square, that is equal 9q square. That we can write 3 into 3q square, that is equal 3m. Since m we are taking as 3q square. See, observe students, let we take a square of this one. Let us we consider first form of this integer 3q. Squaring on both sides, a square equals to 3q whole square, that is equal to 9q square. 9q square we can write 3 into 3q square, that is 3q square. Let us we take m is equal to 3q square, then become 3m. So first form is proved. So if you take case 1 3q, it becomes 3m. Let us we take case 2. In case 2, yes, let us we take a is equals to 3q plus 1. SOBS, squaring on both sides, equals to 3q plus 1 whole square. What is a plus b whole square form? 3q square plus 2 into ab form plus b square. That is equals to 9q square plus 6q 2ab plus 1. Let us we factorize here 3 students. We can write 3q square plus 2q plus 1. Let us we take this one as m. 3m plus 1, where m is equals to, since m is equals to 3q square plus 2q. See students here, first form let us we take a is equal to 3q, that is equal squaring on both sides. So we got a square is equal to 3q square. Then after we have 9q square. 9q square we can write 3 into 3q square. That is equal 3q square. Let us we take m, some integer. M we can take as 3q square. We got 3m, which is first form. Then after let us we take second case, that is 3q plus 1. Then squaring on both sides, SOBS. I already said squaring on both sides, we can write SOBS. 3q plus 1 whole square, it is in form of a plus b whole square. Expand by using a plus b whole square, which you learned in previous class. A square plus 2ab plus b square. It is b square. 1 square. So we have 9q square plus 6q plus 1. Factorize 3 from this. 3q square plus 2q plus 1. Let us we take this one as m. 3m plus 1. Since m is equal to 3q square plus 2q. This is the form. We proved 2 forms, students. So as per the given problem, for square of any positive integer, we have to prove it is in form of 3m or 3m plus 1 for some integer m. So first 2 cases over. Now second case we are discussing about when 3q plus 2 is there. See, understood friends? Yes, third case. Now let us check in third case also. Let us prove it is true for third case also. Yes. So let me take a is equal to 3q plus 2, again squaring on both sides. SOBS. A is equal to 3q plus 2 whole square, that is equal to 3q square. A square plus 2ab plus b square. We have it. Yes friends? Yes. Concentrate here. So now just you go through stepwise. 9q square plus 6q plus 4, that is equals to, again for our convenience to get the form, we can write 4 as 3 plus 1. Factorize 3 from these students. So we have 3q square plus 2q plus 1 plus 1. Let us we take this one as m. 3m plus 1. Since m is equals to 3q square plus 2q plus 1. Therefore, we can conclude that square of any positive integer is in the form 3m or 3m plus 1. So hence proved or not? Yes. See students, case 1 we took squaring on both sides, we got 3m. Case 2 we took a is equal to 3q plus 1 squaring on both sides. After assuming this one as m, it is in form of 3m plus 1. Third case, let us we take a is equal to 3q plus 2, squaring on both sides we have, but for our convenience to prove 3m plus 1 form, 4 we can write as 3 plus 1. Is it wrong to write 3 plus 1? Yes. From this factorize 3. Then this you consider as m. Since m is equal to 3q square plus 2q plus 1. Then therefore the square of any positive integer is in the form of 3m or 3m plus 1, where m is an integer. So hence verified. So students, go through this in this manner. So let us consider three forms. First step we have to write by Euclidean lemma. We can write any positive integer is in the form of 3q plus 1, 3q plus 2. Why we are taking 3q only means we have to prove 3m or 3m plus 1. That is why whenever we have to prove multiples of 3, better to take 3q form only. When we take multiple of 2 or 4, better to take 4 or 2. In that manner, that is the easy way to prove. By Euclidean lemma, we proved these all. It is possible in the form of square of any positive integer is in the form of 3m or 3m plus 1, where m is an integer. So this is the way to solve the problems by using Euclidean lemma. These are the applications of Euclidean. Yes, students. Previously we discussed some applications of Euclidean lemma. Let us discuss one more application of Euclidean lemma. With this we conclude this exercise, and then we'll start next exercise, which is based on fundamental theorem of arithmetic. The given question is, use Euclidean lemma to show that the cube of, in previous problem, square of the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8. So we have to prove cube. Previous problem we proved square, students. Same process. We will take first by solution. I'll start. Let by Euclidean lemma or Euclid's division algorithm. Euclidean lemma or division algorithm, both same. Division algorithm, we can write any positive integer in the form of 3m, 3q or 3q plus 1 or 3q plus 2. Here also we are proving 9 is one of the multiple of 3. That is why we are taking 3q form. Same process, students, where q is integer. Z means integer. Q is an integer. So now let us take case 1. Same process, students. Case 1. Let us take a is equals to 3q. First case. Here cubing on both sides. Before squaring, cubing on both sides. Simply we can write COBS also. A cube equals to 3q whole cube. That is 27 q to the power of 3. So a cube we can write 9 into 3q to the power of 3. That is 9m. Since m is 3q to the power of 3. So first form is proved. Yes, students. Let us take the first form of a positive integer, which is 3q. In general, we can write by Euclidean lemma, we can write any positive integer in the form of 3q or 3q plus 1 or 3q plus 2, where q is integer. Why 3 only means? Because we have to show cubing is 9m plus 1, 9m plus 8. Better to take a multiple of 9. Divisor of 9, that is a multiple of 9 is 3. So first let us we check for first condition. Let me take 3q, cubing on both sides. So we have a cube is equal to 27q to the power of 3. 27q to the power of 3 we can write it as 9 into 9 into 3 q to the power of 3. This let us we take m. So when we consider m is equal to 3 q to the power of 3, it becomes 9f. First form 9m, first form is proved. First case is over. Now second case, we are dealing with second case. Let we take a is equals to 3q plus 1. Again cubing on both sides. That is 3q plus 1 whole cube. So a plus b whole cube form, you know students, a cube plus 3a square b plus 3ab square plus b cube. What is expand form of a plus b whole cube, students? A plus b whole cube equals to a cube plus 3a square b plus 3ab square plus b cube. This identity we are using. Here a is nothing but 3q, b is nothing but 1. A cube plus 3a square b plus 3ab square plus b cube. Now we know 3q whole cube value 27q to the power of 3 plus 3q square value 9, 9 3s are 27q square plus 3 3s are 9, 1 square 1, so 9q plus 1. Let us we factorize here 9. We factorize 9 students, 3q to the power of 3, 3q square plus q plus 1. Let us we take this one as m, 9m plus 1. So first form is over, second form is over. Since m is equals to 3q to the power of 3 plus 3q to the power of 2 plus q. So second form also proved. See, observe students, second form also proved. So first form 9m, second form after simplifying, after applying this identity 9m plus 1. So where concentrate here, where m is 3q to the power of 3 plus 3q to the power of 2 plus q. Let us we check. Well, let us we prove third form. What is third form? 9m plus 8. So let us we take case 3 students. These all problems belongs to exercise 1.1. With this we will conclude. So let us we case 3. Let we take a is equals to 3q plus 2 because third form. Now cubing on both sides, COBS. So a cube is equal to 3q plus 2 whole cube, which is in form of a cube plus 3a square b plus 3ab square plus b cube. Here a is 3q, so b is 2 students, so 3q whole square into 2 plus 3ab square. So we have plus 2 cube. Then after we have 27q to the power of 3 plus 3q square 9, 9 3 is 9 27, 54q to the power of 2 plus we have here 4 3 is 12 3 is 36q because q only plus 8. Now we need to prove another third form, that is 9m plus 8. That is why let us we factorize this total here 9. You can do another way in textbook. Some textbook they make you another way by taking q like that. That is up to you. So here 9 6 is 54. So 6q square plus 4q plus 8. This total value is m, 9m plus 8, where m is an integer. So we can conclude that it is cube of any positive integer in the form of 9m plus 1, 9m plus 8. At the last, write conclude statement. Students, once again I am repeating, without conclude statement your problem is not completed. So you have to write what is conclude statement. Therefore the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8, where m is an integer. See students, to find 9m plus 1, 9 plus 8, we took here q. but the process will be same. With this problem, exercise 1.1 is over. I mean, part 1 of real numbers is done. You'll get some home assignment regarding this part 1 and 2, and part 3 for next class. You'll get home assignment. Please complete it. Complete and maintain one classwork. Do go through proper revision, whatever the topics so far covered. Thank you.